Hi, my name is Amy Sullivan, and I'm the current Vice President of AAAR. It's my pleasure to welcome you to the 27th in our monthly series of AS&T lectures. This is a new initiative for AAAR being supported by the Freelander Memorial Fund. So with these lectures, we hope to highlight the amazing research happening in our community, to tie our journal to other activities, and also give us a chance to all come together outside of the annual conference. So each month, the editors of AS&T select a high-impact journal article to be presented by its authors. These lectures are being recorded and will be later posted to AAAR's YouTube channel, which you can access from the AAAR website under the Events tab. In addition, these lectures are being hosted by one of our student chapters. And so I want to thank you all for joining us and everyone who's helped to make these happen. And with that, I'll turn it over to our student chapter from the University of Maryland, College Park to get it started. Thanks.
Hi, everyone. My name is Naheen. I am the current student chapter president of AAAR for University of Maryland College Park. And today I have the honor and pleasure of introducing Dr. Hagen Telg. Dr. Telg is a research scientist at NOAA's Global Monitoring Laboratory and CIRES at the University of Colorado, Boulder. He obtained his PhD in solid-state physics from the Technical University of Berlin in Germany and embarked on his U.S. journey as a postdoc fellow at Los Alamos National Laboratory in 2010. Transitioning into atmospheric sciences in 2013, Dr. Telg initially focused on aerosols from the perspective of instrument development, and later he increasingly shifted his attention to data product development and analysis of long-term data records, while maintaining his dedication to aerosols. Today, he will be discussing aerosol optical properties calculated from size distribution measurements. So I will hand it over to Dr. Telg.
Hey, hello, everyone, and thanks for coming so plentiful. And I want to thank first, of course, for this nice introduction. And I want to thank the editors for choosing my work so I can present it here and to such a broad audience. So let me share my screen. Okay, so today I'm going to talk about aerosol optical properties and how to derive those from size distribution measurement and what the uncertainties are that are involved in such an effort. And I don't know how it is for you, but uncertainty study always triggers this involuntary yawn in me, or at least it used to be, but this study actually changed my mind, and I had a lot of fun digging into all those instruments, the techniques, and the methods, and playing with new models. So I hope I'm able to convey this the joy I had during this study. So I will start with the introduction to the whole topic. And then I will introduce you to all the key uncertainties, including the instrumental uncertainties, the limitations due to the theory, in this case, me theory, and then also how the different microphysical properties of our aerosols are affecting measurements as well as the calculations. Then I will describe how I propagate those uncertainties using the Monte Carlo method. And then finally, of course, discuss the results. So why should we all be interested in aerosol optical properties? And the main reason is, of course, the aerosol direct effect on the Earth radiative budget, here shown on the, here illustrated on the right, where we have the part that is scattered back into space, the part that is absorbed, and then also, of course, how much makes it to the ground. And there are three aerosol properties that are necessary to describe this aerosol direct effect, which are the scattering coefficient, which describes the overall scattering. So here on the bottom, I show just for a single particle how the scattering might look like. So We have all the scattering, that's which is described by the scattering coefficient. Then the asymmetry parameter, which is more describing the directionality, which is nicely seen here, and which of course then will help us understand how much is scattered forward and reaching the ground, or how much is getting back into space. And then the last property is the single scattering albedo, which describes the absorption of the aerosol particles. But today I will only focus on one, which is the scattering coefficient. So I will ignore all the other ones. In principle, you can measure those properties directly using nephelometers and athelometers, and that is done all over the world on a routine basis. For example, the NOAA's Federated Aerosol Network, which is run or partially run by colleagues from my group, which does these type of measurements. But alternatively, you can also derive your optical properties more from the bottom up, where you use the microphysical properties of your aerosols. And so what you would do is you collect somehow your microphysical properties, like particle size distribution, refractive index, particle shape, but you name it, could be many more. And then you use some type of a theory and model to calculate your optical properties. And but why would you do that? The main one of the reasons is, of course, because when you have those microphysical properties, you can evolve your aerosol, and physically as well as chemically. And that is, of course, important for modeling. And indeed, the modern general circulation models, climate models, are increasingly into using microphysical properties to propagate the aerosols, and in turn, of course, also propagate the radiative effect of those properties. So if you want to engage in this path, then you, of course, want to make sure that you understand the whole process correctly. So usually this is done in closure studies. So you have, on the one hand, you have an observation, or you have two sets of observations. On the one hand, you would have, in our case, the aerosol optical properties. On the other hand, you have the microphysical properties, and then you have your theoretical model, and you want to make sure that they are the same. And it was such a study that made me do this work. And in that study, I struggled to get them to agree within the previously assumed uncertainties. And it regularly and excessively overestimated or exceeded those confidence intervals. So, and also they were almost 20 years old, those studies. So I thought it's time for a new approach with more recent, more recent publications that came out. So, so I want to set now a little bit the scene of this study, and I want to, for that, I go back to this slide I just showed earlier, and want to give it a little bit of reality check. So usually, you do not measure all that many aerosol microphysical properties. The most common one is the particle distribution, but the other ones are rarely observed, and they often have large uncertainties. And especially if you do not have any information on the particle shape, then you might as well use a rather simple theoretical model, which is usually the me theory, to describe your optical properties. And so this brings me to the first boundary of this work, or constraint, is I will discuss uncertainties resulting from using me theory to calculate scattering, and only from size distribution measurements, which is the most common, or a very common thing that is found in the literature. Another confinement is the location. Aerosols are known to be very variable, not just in time, but also with respect to the geographic location. And so instead of, it would be very hard to do that, to do a study like this that is valid everywhere. So I pick a particular location, which is the ARMS, the atmospheric radiation measurement, a southern Great Plains site, which you can see on the map on the right, is located in central northern Oklahoma. And the reason why I picked this particular site is, for one, there are a lot of different instrumentations that are run on a long-term basis. And also that's a place where I wanted to do the closure study, of course. If you want to measure size distribution, there's basically not a single instrument that can measure the entire, or let's call it for this purpose, relevant for optical properties, the size distribution. So you have to combine different observations, and a very common combination is which is also present at SGP, is the scanning mobility particle sizer and the aerodynamic particle sizer. And where the SMPS, the scanning mobility particle sizer, measures in this particular case at SGP up to 750 nanometers, and the APS is measuring for above that. And right, and what I will do is I use this particular size distribution throughout the whole study. So this is my exemplary size distribution, and you will see it quite a lot. So it is the average over the year of 2012, measured as measured at SGP with those two instruments. And then I will do a further set a further boundary, and that is, I assume that the SMPS, it's actually a very important simplification for this study, and that is that the SMPS measures the accumulation mode particles, and the APS is measuring the cause mode particles. And why this is so important is, first of all, accumulation mode and cause mode particles have different origins, and therefore they have different microphysical properties. And therefore this simplifies this study a lot if I can now treat the SMPS measured accumulation mode on one side and the APS measured cause mode particles on the other side independently. It's a nice simplification, and it has another benefit that is that for this particular study, I can, I only will present the SMPS part. But I forgot, I wanted to, of course, first motivate why this is a good choice, a good approximation. And as you can see on the right in the size distribution, I added now the contribution of the cause mode here and the accumulation mode, given by these dashed lines. And while in the number concentration size distribution representation, it might not be that obvious that this is a good motivation to split it here. When you now calculate the scattering for the different, as a function of the diameter, then you end up with this orange picture here. A second. With this orange graph, and you can, I again showed the contributions of the accumulation mode and the cause mode by these dashed lines, and now it is, I think, pretty convincing that to split the size distribution at this diameter at 750 nanometers, and there's only little contribution of the accumulation mode to the larger particles, to the APS measured side, and the other way around. Okay, so as I said, I will only focus on the SMPS side today, and that is very convenient because I would otherwise most likely run out of time. And also, there's a lot of repetitiveness, a lot of, I would have to repeat myself a lot. So that's not very conducive to the attentiveness of the audience, I assume. So the last part of the introduction is the uncertainty propagation that I will use in this study. And that is the Monte Carlo approach, more a brute force approach. The reason why I use that over a more classical approach is that the classical approach is very convenient for simple problems, but the more complex a problem gets, the less adequate it is, and also and the more adequate such a Monte Carlo approach will be. And so the way the Monte Carlo approach works is you, instead of using the uncertainties for all your variables that are carrying uncertainty, you now get a distribution, a probability distribution shown here on top for each of these variables. These distributions are, of course, according to their uncertainties, but also they have more information. They don't need to be normal distributed for this first for the x1 here. They can also be uniform distributed or log normal or other other distributions. So in our case, of course, those parameters here on top would be like instrument uncertainties due to changes in the microphysical properties, and so on. And then in the next step, you take always one set from these distributions, one random set, and you apply it to a function. And that function needs to the dependent variable that you get from this function is, of course, the function, the parameter of interest. In this case, it would be the scattering coefficient. And then when you repeatedly take random sets of these variables and feed it into your model, then eventually you will end up with a distribution of your dependent variable, a scattering coefficient, that then you can do your statistical analysis on, including your uncertainty estimate. Okay, so in the next part of my presentation, I will now focus on how to derive all those and distributions, starting with the instrument part. So I obviously will only discuss the SMPS because the APS I skipped that part for reason of time. And so the mobility the scanning mobility particle sizer is the general principle of it is how particles are drifting in an electric field, so charged particles, obviously. And the way that is achieved is you start with introducing some charge distribution on your particles, which is done with these neutralizers, and then it enters the instrument, the main part of the instruments, and then when it enters into the electric field, all these charged particles are starting to drift, and only particles that drift by a very particular amount will then enter these slits and eventually get counted with a condensation particle counter. So the amount that they drift is a function of the voltage and the electromobility, shown in this function. Then the electromobility is a function of the diameter, and so the particle diameter and the number of charges on the particle. And since we know a little bit about the number of charges based on what our neutralizer is doing, we can then get the diameter as a function of voltage. And to get the size distribution, we would only scan through the voltage and then get our size distribution after applying a rather sophisticated transfer function. So it's not as simple as the three equations here might suggest. And you can, of course, imagine many sources of uncertainty in such a complex system. And it would be quite a feat to get a to get a quantitative, meaningful value out of this. But luckily, there's an alternative, and that is multi-instrument intercomparison studies, and which in fact have been conducted and by this group here on the left. So there's a reference here on the left with probably the longest title I have ever seen. But on the top right, I'm showing some of those results that are presented in this paper. And so it shows the size distribution, in particular, the volume distribution here of these 7 different SMPS instruments. And you can immediately see that, especially for the larger diameters, they deviate by quite a lot. And as you will see later, it's quite important to not just now take the average of all of this and assume that to be the uncertainty. It is important to consider the size dependence of this deviation. And so how we do it is we take the mean of all those graphs here and assume that that is the real size distribution. So we assume that that has a counting efficiency of 1. So we normalize all those graphs by the mean, and then the distribution of all those graphs around the mean are then our counting efficiency. And how we apply that then in the Monte Carlo approach is we simply take a standard normal distribution like shown here. And then if we pick one of those values, let's say 1, then we would take the size dependent counting efficiency that is according to 1 standard deviation and apply that. This paper was also dealing with a sizing precision, and which was not size dependent. So we just used the relative standard deviation that was reported and use the according normal distribution for our probability distribution. So in addition to these more intrinsic instrument uncertainties, we can also, unfortunately, assume uncertainties due to imperfections of our particles. In particular, we have to assume that particles are not always spherical. And the electromobility is, in fact, affected by the shape of the particles. Actually, most measurements are one way or the other affected by the shape of the particles, and therefore, to get around that or to somehow describe that, you would use the equivalent diameter. So the SMPS is not measuring just the diameter, but the mobility equivalent diameter. And what we will use later for our optical property calculations, for that we will need the volume equivalent diameter. And luckily, there's a relationship between these two, which is shown here on the right, where you can describe the mobility diameter as a function of the volume diameter if you consider the shape of the particle, which is here the dynamic shape factor. It's given by Xi, and then which you can then express as the geometric shape factor, which we will need for the optical property calculations, which is given by phi. And yeah, just to say what this geometric shape factor is, it is basically the ratio between first of all, it assumes that you approximate your particles as spheroids, like these oblate and prolate spheroids. And then the geometric shape factor is given by the ratio between the longer axis and the shorter axis, and -1. So and how we now would consider that in our Monte Carlo approach is, first we have to find, of course, a distribution of this. And typically the accumulation mode particles are usually considered spherical. And there's only a handful of observations or studies that study the shape of those particles, and they found that they're actually not all that spherical. And they, as you can see here on the left, they can have quite a lot of different shapes, and they estimate the asphericity, the particle shape factor to vary between -2.4 and 2.4, which corresponds roughly with a ratio of 1 to 3. They also found that the distribution is not a normal distribution, but rather resembled such a uniform distribution. Okay, so much about the instruments. In the next part of the talk, I will talk about how to calculate the optical properties from this, and what the sources for uncertainties are here. And so let's remember that I'm dealing with me theory, like what are the uncertainties from when you use me theory. And so the definition, or the shortest definition of the me theory, is that the me theory is a mathematical description of how light is scattered by uniform spherical particles. So we already see that we will most likely run into an issue here, because I already mentioned that particles are not that spherical. And but let's first discuss how you would use me theory to get your scattering coefficient. So on the top right, I'm showing the scattering cross-section of particles as a function of particle diameter. And what you get is this often referred to as a me curve. Then in the next step, you would use that me curve and convolve it with the size distribution, and what then gives you this scattering coefficient distribution. And then if you just integrate over the scattering coefficient distribution, you get your scattering cross-section. And when it comes to our uncertainties, when I go back here to the top, you can describe the me curve as a function of the diameter. We already talked about the uncertainties of our diameter measurements, so that's dealt with. But it's also a function of the refractive index and the wavelength. So for the wavelengths, we only use the 550 nanometers and keep that fixed. But we can expect uncertainties because of variability in the refractive index, the real as well as the imaginary part. And this is a measurement that is not particularly often done. And also, if it is done, then it's pretty uncertain. Here on the right, I'm just showing how the me curve is affected by the refractive index, by the real part of the refractive index. You might notice that the smaller diameters are more affected than the larger ones, where those three graphs are collapsing almost. Okay, so how do we get our expected probability distribution, our uncertainty for the real part of the refractive index? And this can be done with chemical composition measurements, or based on chemical composition measurements. Luckily at SGP, there is this ACSM, the Aerosol Chemical Speciation Monitor, which measured during the year of 2012. And the ACMS is measuring ion concentrations, and you can use those to estimate electrolyte concentrations, and you can use those to estimate your refractive index, just the real part though. And so we did that for a year worth of data, and then looked at what the variability, the probability distribution looks like. And it is shown down here, which is a normal distribution that is centered around 1.5. When it comes to the imaginary part of the refractive index, we have to use a different instrument, and there's another instrument at SGP that is measuring on a routine basis there, which is the aethalometer. I mentioned it earlier. It's a rather simple principle. You just run your aerosol through a little filter, like shown on the right here. And then as more and more aerosols or absorbing aerosols are depositing on the filter, you will see a slow darkening of your filter. And based on this darkening, you can estimate the absorption. If you then also consider the size distribution and the scattering coefficient that are measured, then you can estimate the imaginary part of the refractive index, which we again did for an extended time, and which resulted in this probability distribution you can see down here. Note that this is a log normal distribution, which we found, and it is centered about 0.013. And then, as I mentioned earlier, we are running into this issue that the me theory is assuming spherical particles, and our particles are probably not spherical, so we are violating that assumption. And the only way to get around this is to use a more sophisticated theory. So with the theory of our choice is the transition matrix method. And the difference now is to the me theory is that we are now considering the oblate and prolate spheroids instead of spheres. And also they need to be randomly oriented. By the way, the transition matrix method is not necessarily, you can use arbitrary shapes. You don't have to use oblates and prolates, but this is an approximation that makes these calculations reasonable, the computational effort. So on the right, I'm showing again the me curve here on the top. And then on the bottom, I'm showing the result from the T matrix calculations. These results are now normalized to the results for the sphere. So basically, I normalize this by a curve that looks identical to this. And therefore, at 1, this is the spheroid axis ratio at 1, where we have spherical particles, and everything is 1. And then everything around it is the deviation from that. And you can see that the deviation can be quite substantial. For example, here where we have a ratio of, 4 and 5, we get a ratio to the spherical particles of 3. So that's quite substantial. And of course, we now don't plot that as a function of diameter, but as a function of volume equivalent diameter. So we do not need to develop another distribution here. We, of course, for these aspheric properties, we use the very same distribution like the one we used above for the measurements. Okay, this brings me now to the Monte Carlo approach. I will start with how the model works, and then we'll apply all those random variables from our probability distributions. So on this picture, I now will present the function part here of the Monte Carlo model. And I'm starting with the particle size distribution. It's again the same I showed earlier. And in the first step now, I will take a random value of the diameter precision and just shift the size distribution accordingly. In the second step, I take a value from this standard normal distribution and apply accordingly a counting efficiency, which is just scaling our size distribution. Then in the next step, I take that already changed size distribution and converted from our mobility equivalent diameter to the volume equivalent diameter, using a particular shape that I plug into this formula, which is effectively, again, just a shift of along the diameter axis. And the resulting size distribution, then I plug into the T matrix calculation, which in addition take now values from our imaginary and real part of the refractive index, and from the asphericity again. And it's important, I of course have to use the very same value here of the asphericity as the one I used earlier when I did the conversion from mobility equivalent diameter to volume equivalent diameter. And that gives me then the result. So here just a brief repeat. I have all those different probability distributions, and now I take random values of each of those, plug it into my model, then I get one value for the scattering coefficients, and then I do that thousands of times, and eventually I get a distribution for my scattering cross-section, which is now one of my final results, and from this I can derive my confidence interval. And so first of all, is this distribution is a log normal distribution. So we expect the confidence interval to be asymmetric around it. And the confidence interval, if we take the 95% confidence interval or the 2 sigma, then we end up with minus 50% to plus 100% roughly, which is of course significantly larger than any of the previously assumed estimates. And now I'm getting back to also to the APS, to the coarse mode part. I just want to show you the results, even though I did not introduce any of the uncertainties involved. And first of all, while all those distributions look pretty similar, they are quite different. For example, the asphericity is twice as big, because it is well known that coarse mode particles are more aspheric. And then the refractive index is quite a bit larger. And also we have one additional parameter that we have to consider, which is the density. Okay, so I do the same thing. Thousands of different combinations of all those parameters give me my final probability distribution, my uncertainty for the scattering coefficient, and it looks almost identical. So now I have on the bottom is for the coarse mode. So it's again minus 50 roughly to plus 100%. And if we now add the two together to get our overall uncertainty, we expect a little bit a smaller value because those are two independent parameters. And we still end up with minus 40 to plus 70% confidence interval, which is still significantly larger than the previous plus minus 20%. So while this is by itself, of course, already an interesting result, and what would be even more informative is if you look at which of our uncertainties contribute to the most to these overall uncertainties. And the nice thing about the Monte Carlo approach is you end up with this vast amount of values, this huge parameter space, and you can now model that just to get a differentiable function or description of it, and then you can take partial dependencies. So I've done that using generalized additive models, which is a quite convenient tool to do this. And you will recognize all these plots here. Again, our parameter, the probability distributions in gray. And in addition, I now give in these blue lines our partial dependencies or our sensitivities. And the steeper those lines are, the more sensitive is the overall uncertainty on this parameter. And to visualize this, to make it more apparent, I now convolved our probability distributions with that sensitivity. So all those blue areas you can see in all those plots are now giving you an idea of how much this uncertainty, the uncertainty of this parameter contributed to the overall uncertainty. And there are two that stand out significantly. And that is, of course, here the counting efficiency and the asphericity. And it's the same thing for the coarse mode, by the way. And again, it's a counting efficiency and the asphericity. Even though the asphericity is twice as big for the coarse mode, and also the counting efficiency, I mean, the whole instrument is a different instrument. Still, it's the same picture. So I want to just address those two uncertainties and why they are so big, or what could be done about it. And when it comes to the counting efficiency, it's a very uncertain coincidence why that is so huge, especially for the SMPS. And that is better understood if you look again at the counting efficiency as a function of diameter. And so if I now plot the scattering coefficient as a function of diameter, then you will see that particularly for the accumulation mode, and now most of the light that is scattered coincides with this increased counting efficiency uncertainty, which is quite unfortunate. And while it doesn't look as bad for the APS, especially the peak here coincides actually with this minimum, still a lot is, of course, within these enhanced counting efficiency uncertainties. So a potential solution for that would be to use a different measurement. For example, optical particle sizes, they are known to work well in this regime, but you still would want to do, of course, a similar uncertainty study to be sure that it is really better. Then another thing is, of course, I mean, that's easier said than done, that maybe some of the instrument developers could focus a little bit more on this size range, because I think a lot of focus is actually on the smaller diameters because it's more relevant to chemistry. But yeah, if you hear this, please concentrate more on this size range. It's more important for optical properties. And then the other one, the asphericity. Yeah, that's, of course, a hard one. But I think one reason why this is so big is that there's just not enough measurements, not enough constraints of these values. So if just more measurements would be done with respect to these to the asphericity, then we might find that it's actually more spherical than these few studies showed in lab environments. So I think just more observations would be great and would help. And then another thing is that because of these equivalent diameters, you could, if you overlap a lot of different measurement techniques, there's a way to derive and gain information on the particle shapes. So that would also be helpful. Okay, this brings me to my summary. I presented a uncertainty study of aerosol optical properties that were derived from size distribution observations under the use of mean theory. I discussed all the involved uncertainties, including the instrument uncertainties, but also how aerosol microphysical properties affected our measurements, and then also how those microphysical properties affected the calculations of our optical properties. So then I introduced the Monte Carlo uncertainty propagation, and finally found that the scattering coefficient confidence interval need to be significantly larger than what was previously estimated. And then I also identified that the counting efficiency and the particle shape are the main culprits to our overall uncertainty. And with that, I want to thank you all for attending and for your attention.
Thank you, Dr. Telg. That was an incredible talk. I learned a lot more about Monte Carlo as well as its applications to things like, these properties. We have time for questions. So if anyone would like to ask a question, feel free to unmute or drop it in the chat.
Can I ask a question?
Yes.
Okay. First of all, thank you very much, Hagen, for this wonderful lecture. Of course, it was quite interesting for the people who are working in the specifically in atmospheric environment, atmospheric aerosols field. So, my question is, of course, these detailed uncertainty studies are associated with these scattering from the aerosols. In comparison to the studies you have made with these me theory, and so, but these studies are quite important when you are using these filter-based method. For example, you already mentioned this ethylometer, right? However, the people who are dealing with photoacoustics, in which this scattering actually does not participate, and the source apportionment and the other optical properties, they are dependent upon the aerosol absorption and their correlation with the size distribution. So my question is this kind of Monte Carlo simulations are good for the absorption uncertainties as well?
I mean, in principle, you can apply it to any type of propagation, uncertainty propagation. So it's a general uncertainty propagation study. You can apply it to everything. It is more about how carefully you choose your distributions and how sophisticated you make your model that you use in the Monte Carlo approach. So what you're referring to, I mean, I think I mentioned what you're referring to on this slide, I assume. And I did a simplified approach here, but if you want to do it more thorough, then you could just do a Monte Carlo just for that part by itself, of course. I don't know. Does that answer your question?
Yeah, of course. Thank you so much.
Okay, thanks.
There's someone with their hand raised.
Simone.
Simone.
Hi, very nice talk. Thank you. My question is, obviously you took a lot of data. I was just trying to understand a little bit of the origin. It's very comprehensive and so on. And those of us who do experiments in some of these devices know that the uncertainties are very large, where you transition from the optical range to the nanoparticle range, and also when you go from non-volatile, solid particles to volatile particles, because there's little data, because obviously if they're volatile, it's difficult to get data from ethylometers, for example, or impossible.
Oh, yeah.
And if you have, let's say, particles that are in the middle optical range, so they cannot be detected optically because they're just below a micron or around a micron. And the other techniques that you might use for solid particles also don't work. So there's a total no man's land there for a lot of essentially all the nucleation particles for ice and so on, just because none of the techniques seem to work. But I'm just curious, whether that's something that was in your mind, because obviously you took a data set from particles that were either solid or could be used in certain types of instrumentation.
I mean, you're basically opening a whole other can of worms here, I guess. I mean, I think it's a good question. I think there's even more variability probably in all those things that I presented, and I totally acknowledge that. I think you can. It would be probably nice to just expanding this more and more, and hopefully also narrowing it down in some sections, and then considering. I mean, the whole like the most particles are probably also not uniform, and they might be core shell, and I do not treat those either. So I don't know. Does it go in the direction of your question, Simone?
No, the question was more, you had a data set, and I haven't looked in details where that comes from, let's say, of things that have been measured, right? The known unknowns.
Yeah.
But then if we think about, let's say, atmospheric scattering absorption and so on, and the models that we use, some of them will be volatile or not volatile, and spherical, not spherical, I don't know. I was just wondering if you are aware of where that database is in terms of knowledge.
I mean, the data. So you're asking where basically all the data comes from. So this is all available in the ARM archive. And when it comes to focus point, I did not consider this any of those very particular applications. So the general idea was really this closure study I wanted to do. And the closure study, the goal was to to improve it by considering more parameters. But the problem was that I struggled in the first place to even get into these previously considered confidence intervals, and I didn't even know where to start. For example, I did actually include in the closure study the refractive index, and I just didn't see any improvement. So that's when I started. I thought I have to go a step back and see what other things could be causing those large deviations. I hope I answered your question a little bit.
No, again, I just wanted to confirm that, because sometimes I think about, should we do the study, or is this known? And so it's useful to know that there might be some things that we don't know. That whole is particularly difficult because it's so difficult to experiment around the 1 micron range. So
I totally agree.
Okay, we have a couple questions in the chat as well. So I'll start off with the question, what about using optical particle spectrometers?
So yes, I did mention that as a possible solution to this, and I think that should be included. And the reason why I didn't include it in the study is that at that time, when I didn't want to do the closure study, there was no optical particle size at SGP. But in general, I think it would be very interesting, and I totally agree that the optical particle sizes should be involved in such a study.
And finally, there is a question. By repeating an experiment for changing dilution pressure during the SMPS runs, if there's a blue shift seen, what should be done to look further in the study? And they mentioned sampling liquid aerosols.
I don't fully understand it, the question. So first of all, a blue shift. I actually don't see how do I see that? I mean, of course, sampling liquid aerosols would, I would assume that liquid particles are more spherical. So, yeah.
So
maybe maybe that person can unmute and clarify it. It's not really clear to me what the question is.
Yeah. If the person who asked the question is still on, would you please be able to unmute yourself? If not, are there any more questions? Okay.
I think that's it.
Alrighty. If not, well, this session is recorded. And if you have any further questions, I'm sure Dr. Telg would be happy to answer via email. Let's see. And thank you again, Dr. Telg, for this amazing presentation and for your time. Thank you everyone for being here. If you need to come back to this presentation, just know it is recorded, so it will be uploaded. And yes, thank you all very much.
I want to thank you too, everyone. Thanks for coming and have a nice day. To you too, Nahin.